Let's now take a look at the definition of composition of functions. So the composition of a function f with a function g is written as, and I'll give it a new name, h of x. So it's written as h of x equals f evaluated at g at x, or f at g at x. So that's our, remember, that's our notation. That's going to be our initial definition, where what we're going to do is substitute g into the function f. Now, if we actually looked at the domain, in the domain of the final function we get, this h, what happens is the domain of h becomes the set of all x values, where x is the domain of g, and g of x is the domain of f. So what's going to happen is we start with an x. We start with our first input. We plug it in, and it needs to be an input in g because the first place we're going to plug it in is in g. So we take the x, we put it into g of x. That value we get out is now the output of g, but for our composition, it then becomes the input of f. So that first computation we do is actually two things. It's the output of a g function, but we're going to use it as the input of f. And so we plug it into f, and we get an output value, and that output value is an output value of f that came from first computing a g value. So if we now use that to take a look at an example, suppose our function f at x is 2 minus 3x, and a g of x is 1 over x squared. We could do a number of evaluations. So first of all, suppose I wanted to do f at g at 2. What we do is we work, again, from the inside out. So the first thing I do is I compute g at 2. So what I'm going to do is look at my g function, and my g at function was 1 over x squared. And so when I substitute 2 into 1 over x squared, that's what gives me this 1 over 2 squared that we see in the example worked out. And of course we know 1 over 2 squared is 1/4. So now we have f evaluated at 1/4. So now we turn ourselves to the f function, and the f function says take 2 minus 3 times x, 3 times its input. So that would give us 2 minus 3 times the 1/4 we already computed. And if we did the math out, that gives us 5/4. Now, let's do g at f at 2. So now I'm doing it backwards. So now the first thing I compute is f at 2. And so as I compute f at 2, what I need to think about here, and I've got an extra g, is I need to think of doing 2 minus 3 times 2, right? This inside part is my f. And so that's 2 minus 3 times 2. So that's 2 minus 6, or negative 4. So now I first compute the inside piece. I computed f, and that gave me negative 4. Now I'm left with g at negative 4. And so now I go to my g function, which says take 1 divided by the input squared. So that's 1 divided by negative 4 squared. Gives me 1/16. Notice something. F at g at 2 is not equal to g at f at 2. And that's going to be important to us as we move forward. So notice, in order of doing this is very, very important to us. So let's go to more of the general situation. Let's do f at g at x and g at f at x. So if I do f at g at x, again, I work from the inside out. So what I do is I say, okay, inside is g at x, so I'm going to pull out the g at x, and I'm going to put in what g at x equals. So g at x equals 1 over x squared. So now I have f at 1 over x squared. Well, how do I do f? Well, f says take 2 and subtract 3 times the input. So I'll do that, and I'll take 2, subtract 3 times the input. 2 minus 3 multiplied by 1 minus x squared. So the 3 is multiplied by 1 over x squared. And if I just neaten that up, thinking of 3, of course, as 3 over 1, I get 2 minus 3 over x squared. So now let's do g at f at x. So again, work from the inside out. So the first thing I do is where it said f at x, I put in what f at x equaled, and so f at x equaled 2 minus 3x. So I now do g at 2 minus 3x. Go back to my g function. G says take 1 divided by the input squared. So I have 1 divided by the input squared. It is not necessary to multiply that out. We'll just leave it the way it is.